Okay, good afternoon. Uh, for today's lecture of state feedback, let me introduce another control method. Actually still state feedback, but we have an additional action which is integral action. Before I jump into the mathematical derivation of this integral action, let me introduce the reason why we need integral actions. So let's see the simulation before this one, and so I have two modeling. The first one is control of open loop. There's no control, and this one we have control. State feedback control, where we for which we design, we choose controller K1 and K2 and the scaling controller KR. So let me show you the result before, like this, and you can see the performance is quite good. So this curve is for the closed loop control, the feedback control, and you can see the response of lateral motion Y at around 0.3 or 0.4 second. Okay. In order to access the performance or evaluate the performance, let me plot the graph of input and output together. Okay, so let me change a little bit. Well, K1 and K2 actually remember the previous session. I'm supposed to run the main file to generate the constants first actually. So here's 5 parameter. Let me run this first, and then if I run this one again, there is not supposed to have this one. So it's okay. Plot, because I closed the plot too early. Well, let me make the plot of input and output together. So output is the first one, okay, Y1. So I'm gonna merge the signal of Y1 and the input together. So first let me close this. Perhaps I don't need to see this one. I already know that it's stable. Then I disconnect this one. I cannot disconnect it. Maybe on the red one. Cannot. So I just delete it, and also delete this one and bring mux. Okay, bring mux here, and so like this, and this one to the input. Okay, and I don't need 3 port actually, I just need 1. But 1 port has 2 signal, right? 1 port has 2 signal. And this one I don't need. This one also. This one also. and then move these two up. Okay, let me try again. Oh, sorry, actually we are supposed to use Y2, not Y1, right? Y2, not Y1. So not this one, but instead this one. Maybe like this. Okay, and let me run again. Wait, this one is fine, the input, and this one, oh, the black one is correct. Actually the black one is this one, it is correct already, but the green one, the input, I'm sorry, this is the input voltage, but we want to see the reference, we want to control. So stupid, eh? Yeah, we want to compare with the reference, the output and the desired output. Okay, this one is desired output. Yeah, and let me try again. Okay, now you see that the output, actual output, convert to the desired output, which is good. So, and then the question is raised, if this kind of control is already good, why do we need control, integral action? Well, actually this system is good because there's no disturbance. Yeah, there's no disturbance or uncertainty. But in real life, in many cases, disturbance exists. So let me introduce disturbance first. So I move this to the front. It seems like I don't need this one, so I don't need, yeah, I just delete it. Okay, I don't need it, so I can move this a little bit up here. Yep. So where am I supposed to add the disturbance? Okay. What happened with this one? Okay. So where disturbance can occur? Let's say disturbance occur at the state equation. Let's say here. So let me use the add here. Okay. Here and here, and then I have a constant. Let's bring the constant, supposed to be from source, and then constant, this one. So this one, let's say constant is 0.1, maybe 0.2, to see yeah, if we have disturbance like this, what happened? Okay, what happened to the performance? Okay, and port side, problem in port side or type. So maybe this one just needs 0 because it has extra ports. Then let me just give 0. Oh, this one is 2, so I see disturbance. Oh, why this one is 0? I think I delete something and then big mistake, right? One big mistake. I need the state back to here. Yeah. Yeah, it's a little bit time consuming, so this one cannot be used for what happened with this one? I think I cannot use this one, so I use other add block, signal routing or maybe mathematical operation, and then use summation here. Okay. Try again. Port side. So it seems this one does not accept. Okay. Data type, input or sign, number of inputs or sign vector. Data type. Can I use matrix? Size to 1. A little bit trouble. It cannot accept matrix vector, so I will need to add somewhere else. Okay. Let's say the disturbance is at the input. Okay, let's say it's here. Disturbance. Yep. Some. Oh, I have not just one input, but several input here. Yeah, let's say I have disturbance at the input, then what happened? Well, that is too much, right? The disturbance is too much, so it to let's say 0.02. Even just small disturbance, oh, this one also plus. Yeah, okay, let's say I have disturbance, so then we cannot get the actual output the same as desired. It does not converge, right? So we introduce integral action. So the integral action will try to eliminate the effect of disturbance. Okay. Yeah, it's a little bit difficult to build in the SciLab. So here, previously you already learned the controller of state feedback and the scale controller KR. So from here, let me introduce integral action to remove steady state error. As you can see in the simulation, you have the steady state error because actual output does not converge to desired. So here we introduce an additional state variable in our system. We call it the Z, where Z dot equal to Y minus RT. This means Z actually equal to integral of Y minus R dt. That's why we call integral action here. And then if we concatenate the state equation with the new equation here that we just introduced, and so we have this form, okay, AH plus BU Y minus R, and then we can substitute Y by C times X, okay, and then we rewrite in a matrix block, okay, matrix block like this, A times X, right, 0 times Z, C times X, 0 times Z, right, because there's no variable Z in here. And for U, for the term U, we only have V for state equation here, and there's no U for the equation of Z dot. Okay, and then R we can rewrite like this. There's no R for the first equation, so we only have 0, and minus 1 times R here, because R is scalar. We only consider scalar, right? So we write this in this form. Now actually we have state equation again. Just call it. Just call this one. Yeah, this equation as H dot, capital H dot, equal to. Yeah, actually we already have capital A. We already have A calligraph. Now I just call it A capital H times X plus BH times U. So here, yeah, this one just call B B here in the case of capital H, yeah, just call it B times U. No, it can confuse. Anyway, maybe just call A1 and B1 times U, and yeah, this one is just B1, and then this one just call C1, not C. Okay, just call C1 times R. Okay, now let's design state feedback control for state capital H. So we choose U equal to minus K time, no, K, Ki time X and plus KR R. Well, actually this one is not necessary. I'm not going to prove. I think if you are interested, you try to prove yourself. If you introduce this KR, finally you just find that you will just find that KR equal to 0 over 0. What does this mean? Yeah, in the case of scalar, this means KR can be any value. Right? Can be any value, so we don't need, right? So just use KR equal to 0. Just don't use this term, not 0, sorry, but just don't use this term. Okay, no need. Okay, and here, because it is small h and z, then we can have minus k times x plus minus ki, we just say minus ki times z. Okay, and then yeah, because I jumped it before. Well, and then if we substitute u back to here, we can have h dot equal to a1h minus k, just call this k calligraph. Yes, just call this one k calligraph. Yeah, minus b k x plus c1 r. Then h dot then h dot equal to a1, this is the b1, minus b1 k times x plus c1 r. Then we set the condition such that h converge, right? So h converge if and only if eigenvalue of a1, yeah, all eigenvalue of a1 minus b1 k are negative, right? Yeah, just same as before. So we follow the same process. Actually, we can design for K calligraph. So where do I have it? Okay, anyway, it's gonna take time to find K of the integrator. Why? Because now our matrix becomes 3 by 3. Even you just use even you just find determinant, it's gonna take time. So we should use software to find well, how would I say, it becomes third order. It's gonna take time to find it. So I suggest another method. We can just use trial and error on the Ki, right? Okay, but we gonna trial and error K1 and K2 also. Then maybe we don't expect to get a good performance. Well, okay, I think it's better to derive manually. Yeah. Okay, let me show how. Okay, so in order to find eigenvalue of the matrix A1, duplicate, yeah. Okay, so matrix A1 equal to AC0 0 times H and Z. Yeah, just like this. So A equal to what? Let me go back. Where is A? Oops. Where is A? Yeah, here. Okay. Okay, can't remember it now. So we have 0 0 V0 0 like this, and then C is 1 0, and then we have 0 0 0, not of 0, right? And B1 equal to AV0 over B. Okay, AV0 over B, V0 over B, and 0. Okay, then A minus VK equal to like this. Minus AV0 over B, V0 over B, 0, time K1, K2, and Ki, like this. so equal to 1. And so this one same, and this one, what do you have? You have a v0 over b k1, a v0 over b k2, a v0 over b ki. Okay, and this one v0 over b k1, v0 over b k2, v0 over b k3, ki, and you have 0 0 0. Okay, like this, and this one same, and then you subtract them together. You have a minus b k equal to minus a v0 over b, v0 minus a v0 over b k2, for this one k1, and then a v0 over b ki, and this one minus v0 over b k1 minus v0 over b k2, v0 over minus v0 over b ki, and then this one 1 0 0, right? This one minus this, yeah. And this a1 b1, sorry, a1 b1. What you can do next, find eigenvalue by definition. Now let's call this a2. So by definition, lambda I minus a2. Okay, to find characteristic equation, you use determinant of this equal to 0, right? And then lambda I minus this, you have what? You have lambda plus a v0 over b k1, and this one a v0 over b k2, this one minus, this one minus or plus, this one is minus, right? So this one become plus a v0 over b ki, and this one plus v0 over b k1, this one lambda plus v0 over b k2, and this one come plus v0 over b ki, and this one minus 1 0 and lambda. Okay, so determinant of this equal to 0. How can you find determinant of this? Well, you can use the one element time its cofactor, right? So for example, this one minus 1 times minus 1 times so here's 3 plus 1 become So the cofactor is minus 1 times to the 4, and then times determinant of AV0 over BK2, lambda plus V0 over BK2, AV0 over BKI, V0 over BKI, and plus lambda times minus 1 power 3 plus 3, which is 6, and times lambda plus AV0 over BK1, V0 over BK1, AV0 over BK2, lambda plus V0 over BK2, like this, and you set it to 0. So from here you can see that the degree of lambda is 3, right? Because you have this lambda times this lambda and then times this lambda, right? Determinant, this times this minus this times this, right? So let me, okay, this one become just plus. So lambda times lambda here, lambda 3, lambda to the 3, and then plus, what about lambda square? Where can you have lambda square? Yeah, this lambda times this, and this lambda times this. So AV0 over BK1 plus V0 over BK2 times lambda, and then plus this times this, AV0 square over B square, and K1 K2, and then this times this, but minus A V0 square over B square K1 K2. Oh, this one cancel, but we still have this term. How we can get this term? This one is just minus. How you get lambda? This lambda times this lambda. So this is minus, and this also minus. You have plus. So I have plus AV0 over B Ki lambda, and then plus this times this, V0 over B, AV0 square over B square, K2 Ki, right? K2 Ki, and minus how come one lambda is 0? Okay, look, and then minus this times this, A V0 square K2 over B square K2 Ki. If I cancel this term, okay, I'm afraid I may make mistake somewhere. Okay, yeah, it's gonna spend too much time to find the mistake, I guess. This one consider this one, right? And this one also consider this. So lambda square. Oh, I lost the term lambda square. Okay, anyway. All right. Okay, try this way. Maybe this way to do it manually is a little bit hard and time consuming. You want to, you can try and be careful. So I'm gonna use trial and error method. Trial and error method. It means I still use the same K1 and K2. K1 and K2 here I still use the same, and then I don't need to use KR, but then I tune KI. Control C. So let me just delete that one. Okay. Well, so KR can be any value, so just keep it, no problem. Or you can just remove it and use 1. And then you need KI time the error, and then you put you use integral. So how can I have the error between the reference and the output y? Okay. So I put where should I use it? Okay, let me move this one to the right a little bit, and then I have look at the equation. This one we need this term, and then we need z times ki, right? Z times ki. Okay, so we need z first. I use sum again, but this time 1 plus and 1 minus here. So I have, okay, it should be this one plus, okay, this one minus and this one plus to the reference. Okay. Okay, and here is y. Y is plus. And it is the same as this one. Same as this one, right? Yeah, it back from here. Okay, plus and minus, and then we need integrator. After integrator, we use one gain to tune it, ki, and we're gonna tune ki. Yeah, no. we need to add. I'm gonna put this one more, right? Oh no, it cool. One like this. Yeah. And this one add to this. Okay, and this one call it ki. Yeah, ki we haven't give the value yet, so I'm gonna give the value ki here. Ki just give it 0.1 first. Let's see. Oh, need to run it. Okay, and then I change this one to ki. Okay, and then we need, oops, then we need this term 0 and minus 1 times r, and add with u times b. U times b. Oh, wait, we already know u equal to this. We just need z and ki. Oh, yeah, we don't need to care about this one. Yeah, no need to care about this. Sorry. So I think if we are good to go, then let's run the simulation. Oh, this is good. This is bad. This is going to be bad. Ki is negative or minus ki. Okay. Yeah. All right. So because I use trial and error method, we don't have the desired specification for the transient, right? In order to have the desired transient, we need to derive the equation and compare to standard form for third order. Okay. So it seems this integration is too slow, and then we can increase ki a little bit, say 0.3. Then look what happened. Yeah, it's fast here, but at the same time overshoot is also high. We need to play around with K1 and K2 too. Yeah, like I said, if we don't derive for K1 and K2, then we don't have good performance. But anyway, you have the idea that we can use integral action to eliminate the effect of disturbance. Okay? Like this one, you can see, because of disturbance, you have very huge error, right? Um, Alright, so now you try to simulate this system. Okay, let me brief again. So I'm gonna show you method by using pole placement. So just type here to search your pole placement, and then you can see pole placement here, and then you see the syntax p pole, it means place pole, and then here is a syntax k equal to place the pole for the system with matrix A and matrix B. So now I add more program from the original one. This one for designing controller in the case of this one without integral action. The first method I use tuning, just try 0.3 and got a relatively good result. But now I want to use a different method, which is to use pole placement. So I define A, B, C as a matrix of the original system, and then I use A1 which is A concatenate with C and 0, 0. So but why I use 0 to 1 here? Let me show the state feedback slide here. Oops, where is it? Maybe I already discard everything. Yeah, integral action, where is it? Integral action. I already discard everything. But anyway, why we use this one 0, 0? Because actually our A is A equal to 0, V 0, 0, 0 like this. And then when we concatenate with C which is 0, 1, 1, 0. Okay. And then we need to complete this matrix to become square matrix, right? So this is A, and this is C, and this one is 0, this one also 0, but this one is 0 to 1, right? And so in this side note, I need to use this. Oops, what is this? Yeah, and then B just B and then 0, right? And now I define poles myself, because in order to have a stable system I need to have negative poles. Okay, minus, for example, minus 10, minus 5, minus 3, right? How can I come up with this number? Actually, I try from, you can try from just 1 to 3. If you don't know any number which supposed to be good for the system, try. And now I use K1i, K2i and Kii just to differentiate this case. Okay, so I must modify here a little bit. Now I use K1i instead, and I use K2i instead, and then I use Kii. Yeah. Okay. Then I run it. Now I get the result of the system which is not good, right? Because the pole is too close to 0, right? All of them are negative but too close to 0. So the response is it's hard to explain now because it's third order system, right? And so I tune the pole because I know that the further the pole from the origin, the better, right? So run this and then try this one again. Now it's much better, right? And if you think, well, you may want it to respond even faster, then okay, let's choose this one also -5. Run, save and execute, and run this one. Yeah, it's not so much better. Yeah, I think this performance is not too bad actually. Let's say -10 is say 12, 15. I don't know. It's gonna be better, or maybe this is the best we can have because this is third order system. Oh wow, we can have a faster response actually, right? If you prefer to have overshoot a little bit, then you can choose complex number, but has to be complex conjugate. Two of them must be complex conjugate. Okay, so far so good. Now I think you got 3 ways. The first one, which is the most difficult one, you need to find the characteristic equation in terms of eigenvalue, and then you have third order, and then you can compare to standard third order that I introduced before long ago. And the second method is just to tune Ki directly on the system that we design controller based on state feedback only. And the third method is to use pole placement of the new system, the concatenated system that we introduce, another variable which is the integral of error between reference and actual output. Okay, so far so good. So try please. It's time now. You 1 minute, but I think maybe you can easily finish this. Yeah, I can take 1 or 2 questions you have.
So how about
MATLAB. MATLAB, I think you have the syntax place. Yeah, place. And yeah, same. Use A, B, and then poles. A1, B1 to be precise. Any more question? Okay, so we can stop now.